this next one here, this is going to be on a lot of your quizzes and tests, I'm going to guess. I mean, I don't know your teacher, but this is something that will keep popping up throughout organic chemistry, and that is, what can you draw with this? So let's start with this first one here. We have 3 carbons, 7 hydrogens, and a chloride. Okay. A quick formula for you to know is that if there are no double bonds, no triple bonds, no ring structures, the number of carbons you have times 2 plus 2 equals the number of hydrogens you have. Okay, so for example, if you have C2, so 2 carbons, to fill that in, you're going to need 2 hydrogens for each of them, plus an extra 2 for the ones on the end, right? We could do the same thing with 4 here. Each of these are going to need 1, 2, top and bottom, and then each of the end ones needs an additional hydrogen, right? That makes sense? So that's kind of a general rule. A chlorine, so let's go back to how many valence electrons does chlorine have? It's got 7, so we go around 1, 2, 3, 4, 5, 6, 7. He's going to have 3 lone pairs, and he's going to want to make 1 bond every time. There's always exceptions to random things, but we're just going to stick with that as an always rule. So, note on all of these. So here at number 2, she does it for you, but if you ever get confused, you look at a periodic table. Carbon forms 4 bonds because it has 4 valence electrons. Nitrogen has 5, it needs 3 more, it wants to make 3 bonds. Oxygen, same thing too. Hydrogen, fluorine, chlorine, bromine, iodine, all of those make 1 bond. So if you have a chlorine, a bromine, whatever, it takes the place of a hydrogen. It's the same thing, it forms 1 bond. And so in this rule I have up here, C times 2 plus 2 equals your hydrogens and your chlorine, bromine, iodine, halogens, also known as X. Okay, all of those halogens in that column 7, the group 7, we abbreviate them to X as a generic term. Okay, so if we want to know if there are any double bonds or triple bonds or rings, what you can do is you look at your carbons and hydrogens and other things in here, and you can actually do an equation and find out. With this guy here, we can see there's 3 carbons. If we multiply that by 2 and add 2, we get 8. Right? Okay. And we have here 7 hydrogens and 1 chlorine. So that equates. We're good. What that means is there are no double bonds, no triple bonds, and no rings. So what we can do here is we can draw our carbons all in a row, and we can fill in our hydrogens everywhere except for we'll put our chlorine somewhere. So chlorine can go here, the rest can be hydrogens. Where else could we put this chlorine that it would be different than this molecule we drew up here? So where's another place we could put it? Attach it where? This first C instead. Okay, so carbon, 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 attached to a chlorine, hydrogens, 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 hydrogens. Okay, now what this comes down to is actually, if I took this molecule and flipped it around, it would actually be the exact same thing. So because this molecule is really pretty the same everywhere, having it be attached to the first one or the third one is the same molecule. So that's only one. Where else could we attach the chlorine to? Between. You can attach it to a hydrogen. Well, I mean, you could, but then it wouldn't be attached to a carbon because they can both only form one bond each. So rather than attaching it to 1 or 3, we could actually attach it to the second carbon. So let's draw these. So attaching it to the second carbon here, fill in the rest with hydrogens. And the chlorine can be attached on the bottom or the top. And let's practice drawing these in skeletal form. So this first one here, because there's 3 carbons, we're going to start with carbon 1, up, that's 2, down, that's 3, and then we're going to attach it to a chlorine. So that's what this is. Okay, I can do the same thing here. I can put a chlorine here, up to a carbon, down to a carbon, up to a carbon, but these guys are identical. Okay. Then this guy, if I were to draw him, just make 1, 2, 3 carbons and attach the chlorine at the top. I'm going to skip B and C, and we're going to talk about double bonds and triple bonds and rings and how we figure that out later. I'm going to move on to D because it follows the rule that I told you before with the C3 times 2 plus 2, H equals 8. Okay? So this guy, again, is not going to have any double, triple, or rings. So what's an idea that you have where we could draw out this structure? Okay? And then where are we going to put our hydrogens? Okay, 3 on the first one, right? 2 on the next. How many on the third one? Okay, how many hydrogens have we used? Where did we put the last one? How many bonds does oxygen need? It has 6 valence electrons, which means it needs how many bonds? 8 minus 6. It has how many so far? Okay, and we have a hydrogen that needs a friend, so where are we going to put the hydrogen? On the oxygen. Yeah, there we go. So that's one possibility. Good. We attached our oxygen to to one of the end carbons. What else is a possibility that we could do with him? Think of the chlorine example. Where else could we attach the oxygen that it's different? Good. So we've got carbon, carbon, carbon. Throw the oxygen up here. Fill in the hydrogens. Each side carbon will always have 3 if nothing else is attached. The middle carbon will have how many hydrogens? Good. That's how many hydrogens? Good. Okay. Now, there is another possibility that we haven't talked about, and that is to break up our carbon chain. So these, just a early review here, if you have an OH attached to a carbon, This is called an alcohol. If you have a oxygen in between carbons, this is called an ether. So now where do we fill in our hydrogens? How many on this first one? Good. 3, 2, 3. How many hydrogen is that? Do you need one on oxygen? No, because we already have 2 bonds for our oxygen, so he's happy. All right, that would be it. We didn't talk about this last time. I just dealt with the unsaturated ones, but this is a formula that you can use to find desaturation, or how many double bonds and rings and triple bonds you'll have. So what we have here is this formula. You take the number of carbons times 2, and then you are going to add the number of nitrogens, subtract the number of hydrogens, and subtract the number of halides like fluorine, bromine, iodine. And then you divide all of that. Oh, sorry. And then you still need a plus 2. All of that divided by 2. Okay? Now, the reason for this is, if you remember, we went over this last time, but if you have 3 carbons, how many hydrogens are you going to need to fully fill this out, right? You're going to need 2 for each of the carbons, and then you're going to need 1 on each end. That's why it's 2 times a carbon plus 2. Then what's going on here is an X, or a chlorine, bromine, iodine, works the same as a hydrogen in taking up that space. So you could easily have, a chlorine here, hydrogen, 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 a bromine there, hydrogen, hydrogen, and it would be just fine. So those act as the same. And then nitrogen, if we add in a nitrogen here, carbon, 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 nitrogen. Okay, these are all connected. Nitrogen has a lone pair. So if it's already connected once, it's just going to need 2 hydrogens. So instead of needing 3 when it's on the end, it will only need 2. So rather than being multiplied by 2 like the carbon is, it's just multiplied by 1. If it was in the middle of a carbon chain, it would just need 1 hydrogen. Okay, so it needs 1 less than a carbon normally would, which is why you don't multiply by 2. So you take this and then you divide it by 2, and that tells you how unsaturated it is. So let's give an example here. If we had a carbon double bonded to a carbon, single bonded to another carbon, let's fill this up with hydrogens, okay? We just need 2 here, right? How many here? Just 1. And then how many at the end? Good. Okay, so let's count these up. 1, 2, 3, 4, 5, 6. Okay, so we have C3H6. If we plug this into our formula, we have number of carbons, 3 times 2, and then we're going to add 2. We don't have any halides, we don't have any nitrogens, so we're just going to subtract 6. Okay, so 6 plus 2 minus 6 equals, good. And then we divide by 2. I can put that at the beginning here. Divide by 2, and that equals 1. So that means there is 1 unsaturation. That means we could either have a double bond or a ring. In this particular case, we know it's a double bond because we already drew it. But if this had been a 2, that means it could either be 2 double bonds a triple bond, or a ring and a double bond, or two rings. Does that make sense? A ring counts as one, a double bond counts as one, a triple bond counts as two, and it can be any combination. The formula was 2 times carbon plus 2 minus hydrogens minus halides plus nitrogen, all divided by 2, equals unsaturation. X is halides, so chlorine, bromine, iodine, fluorine. So let's do B then. Okay, so over 2 is 1. Okay, so what does that mean? Right, something is unsaturated, and what are our options for that? What could there possibly be in our structure that way? We could have a double bond. It could be to the oxygen. We'll just stick with double bond. And what's our other option that it could be based off of unsaturation? So to get 2 double bonds, we would have to have at least a 2 here. The other thing it could be is a ring. So for example, if you have them all connected to each other, then there are no ends. So for example, each of these carbons would want 2 hydrogens on them, and you wouldn't have a +2 for the end ones because there is no end. Does that make sense? So each of these would be 2, 2, 2, 2, 2, 2, so you would only need 12. But the formula says that you would have 12 plus 2, anticipating the end ones, and so we wouldn't need those. But for this, we only have 2 carbons to work with and an oxygen. So rings are going to be a little more difficult. Rings are easier if there's like 5 or 6 things to deal with. But we won't completely put that out right now. So let's start some possible structures for this. We know it has 1 unsaturation. So what could this look like? Let's brainstorm here. You mentioned a double bonded to an oxygen. Okay, like that. And then where do we put our hydrogens? Okay, how many there? Okay. And how many on the second one? Okay, perfect. Just so you know, this is what's called an aldehyde. I'm going to start helping you notice these things. This is a carbonyl, and a carbonyl attached to a hydrogen on the end like this is called a aldehyde. You're going to want to know the names of functional groups. So a carbonyl is something that you'll find in lots of different functional groups, but it's really important to recognize. Let's move on to other possible structures. What else could we do with this? What other isomers, structural isomers, can we come up with? That depends on the preference of your teacher. There are dots around the O. I don't always draw them because some teachers care and some teachers don't. But when in doubt, probably should put the dots. You are right. Okay, so putting the oxygen in between the carbons, like this. So one of them needs to be a double bond like this. Is that what you're saying? The one difficulty I would have with this is oxygen would be pretty unhappy because how many bonds does he have? Um, he has 3 bonds, and he usually only likes to form 2. And that comes down to he has 2 lone pairs that he likes to have, and then things start to get a little crowded. So then he wouldn't have 2 lone pairs. This is not impossible, but it's not stable. So probably wouldn't use this one. Where else could we put a double bond? Yes, because based on the degree of unsaturation, it has a double bond or a ring. We've got to put a double bond somewhere. Otherwise, we won't have enough hydrogens to fill this all out. So if we go back to this guy and just tried to fill in with hydrogens, we would need 3 here, right? And 3 on this side. But how many hydrogens do we have? Yeah, so we wouldn't have 2 of these, and then our thing would be uneven, unhappy. It doesn't work. But that's good problem solving. That's how this works. So good. What's something else we can try? Good. Carbons double bonded to each other, and then oxygen attached to one of them. Okay. And then where do we fill in the hydrogens? 3 on the outside carbon. Okay. How many bonds does he now have? Just 2 on him. Okay. Okay, where do we put the next one? How many on that one? Okay. Where do we put the last one? Yeah. He wants to have 2 bonds, so we make him happy. 2 sets of, yeah, 2 lone pairs. We could try something a little non-conventional. 3 membered rings aren't the best, but we could always try him anyways. We could do something like that. And then where would we put our hydrogens? Yep. Do you put the hydrogens, you say? Yes, so you'll put the hydrogens if you're drawing them in the Lewis way or structural formula like we're doing here. If you don't want to draw hydrogens, then you also wouldn't draw the carbons. So the way to draw this otherwise would be like this. Okay, so you can redraw that. Or you can draw like this. That's also an option. You can draw the hydrogen when it's an aldehyde. For this guy here, how would you draw him? You want to take a stab at it? Okay, down to the O. Okay, and then how do you draw in the double bond? Okay, so make another line in here. And then what do you do with the oxygen? We will put its lone pairs on it. We'll also add a hydrogen. Anything that's not a carbon will have all of its hydrogens drawn. So a nitrogen with a hydrogen on it, you would draw those hydrogens. Oxygen, if it's attached to a hydrogen, you'll put those in as well. So I can put in its lone pairs if I want, or I don't have to if I don't want. Okay, what about this last guy? Absolutely, you got it. Triangle with an O at the top. I suggest as you're starting, with these sorts of things, do this way just to make sure your hydrogens you have enough, you don't have too many kind of idea. And then doing like we're doing here, drawing them in their stick form or their skeletal bond line, whatever you want to call them. So let's do the degree of unsaturation formula. Good. Double bond or ring. All right, how do you want to start this guy out? Okay. The chlorine, the nitrogen attaches to the chlorine. It's Cl and then N. It is a chlorine. Okay. Is the chlorine attached to this carbon or is the nitrogen attached to this chlorine? Sorry, this carbon. That's what I'm trying to find out. You're saying carbon, carbon, chlorine, nitrogen? Okay. So the problem with that is chlorine can only bond once. So if we do this, then this guy is unhappy because he's holding on to two people and he can only hold on to one. He's like a hydrogen. So good thought, and it's in order, the same order that they wrote it in, but it just doesn't work, unfortunately. Okay, you give the carbon and the nitrogen 3 bonds. Oh, a triple bond? Um, we could, except for we only had 1 degree of unsaturation. So that would, to have a triple bond, it would require at least 2. So we can only have a double bond or a ring. But we could make that a double bond if you want. That's okay. Do you want to do that? Okay, so we'll do a double bond there. Where do you want to put the chlorine? Okay. And then where do we fill in our 4 hydrogens? Okay, first one gets. Good. Second one gets. Good. Okay. And then nitrogen's happy. He's got 3 bonds already. He's just got his lone pair. Carbon in the middle has 4, and the chlorine just has the 1 that it wants. It's happy. Okay? Cool. Let's draw another one. What else could we do here? Yes. Uh, no, we can switch the hydrogens and the chlorines around. We could put double bonds in different places. The carbons don't have to be attached to each other. We can make a ring. This one actually has lots of possibilities, unfortunately, actually. This is one that I find difficult for tests and things, is they'll say, draw all possible structures, and you think you've thought of all of them, and there was one more. So you just have to kind of like grind the gears of your brain and go, okay, what else could we possibly do to this thing and have it still work? Okay, so carbon, double, double, carbon, and then nitrogen. Okay, then where are we putting our chlorine? Okay, and then our hydrogens. Okay, so how many on that first one? Okay, and on the second one, how many bonds does it already have? Okay, and where do we put the last hydrogen? Good. And he's got his lone pair. Okay, so that's a possible way. What else can you think of? Perfect. So where do you want to put the chlorine? Sure. So we'll pick the first carbon for this one. We can, good. Mm-hmm. Good. Very good. Nope. We can we can put the carbon on the middle chlorine. Sorry, the chlorine on the middle carbon. We can draw him that way. Just put an H2 there. And then don't forget that we can move the chlorine around in the first one. So this chlorine, I can switch with a different hydrogen from the other one. So I can put chlorine attached to this carbon, attached to two other hydrogens, single bonded to a carbon, hydrogen, hydrogen, attached to a nitrogen with, oh, sorry, double bonded to a nitrogen with a hydrogen. And where am I going wrong here? This one. Put too many hydrogens on the middle carbon. And then this guy could also, the chlorine could be on the middle carbon instead. This guy would be H3. Ooh, that was really bad. Getting sloppy here. Double bond nitrogen, hydrogen. Okay, so these three here are all variations of the same thing. We're just moving the chlorine around. These three, same thing. We're just moving the chlorine around. Now, another option we have is moving where the nitrogen is. We could put the carbon and then the nitrogen and then the carbon. Where should we put our double bond? Okay, we'll put it on the right here just for fun. And where do you want the chlorine? On the double bond side or on the non-double bond side? Well, no, but it's another possibility. Point I'm trying to make with this one is there are a lot of options, unfortunately. Okay, so we'll put the chlorine here. We'll put 3 hydrogens on the left. We'll put another hydrogen on the carbon on the right. And nitrogen is happy with 3 bonds already. And then we'll switch the chlorine to the other side but leave the double bonds the same. So chlorine here, hydrogen, hydrogen, and then a hydrogen, hydrogen here. Okay. Now, I'm not going to switch the double bond around because what's happening here is this is symmetrical to the point where if I were to draw this carbon, nitrogen, carbon, and put a double bond on the left, and then if I were to put the chlorine on the left or on the right, so let's just say I put it on the left, putting it on the carbon with the double bond would be exactly the same as this one. If I put the chlorine on the other side, it would be exactly the same as this one. So these are duplicates. And so I won't include those. So these are similar enough that I'm going to box them together. You don't need to do this in general. I'm doing this for your benefit, the boxing similar ones together. And now we haven't come up with any rings, and we can. So one last one that I can think of. Carbon, carbon, nitrogen. And then, let's see here. Oh dear. Chlorine could be on any of these. So that's 3 options. You'd have a chlorine on this one, 2 hydrogens here, 2 hydrogens here. Carbon, carbon. Man, this one's a doozy. Oh, we wouldn't have 3 options because the carbons are identical. Happy day. We have an end. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 options that we can think of. This is not unusual, just so you know. When you start having more carbons, then you can start branching in different ways. So just beware of replicating the same thing. Like if I had put chlorine, if I had to put a chlorine on this other carbon here in the triangle, that would have been exactly the same. There's definitely duplicates, but all of these are different from what I can see. I have been known to make an error though, so. And I could even be missing one for all I know. But yeah. And to be honest, I don't know what your teacher wants because on your teacher's answer key, she did not list very many for A, B, C, and D. Some of them she didn't list any at all. So I'm not sure if she told you guys what's going on with the worksheet, but